So let's talk about hash tables. That's how Ben intros all of his lectures here. So I have this notion. Thingamabob here that I'll go ahead and throw in session for us. Um, that way you guys can see what's going on here and kind of follow along. It is. I'm kind of learning how to use Notion, so a lot of it kind of might feel like gobbledygook. Just kind of bear with me. I do feel like I have a medium grasp of hash tables now that I kind of didn't have before. So there's a good chance that I might be able to answer your questions. So to start here, let's talk about hash tables. I have this guy, and then I opened up a whiteboard here. I guess you guys can you guys all see this whiteboard?
Cory, your Notion's not public.
My Notion is not public. Okay.
Do that after, though. Just continue.
Okay. Can you guys all see my screen, though? You can see my whiteboard here?
Yep.
Groovy. So hash tables are a data structure. They use keys to sort indexes into a table. When we covered hashing in class, we covered it in what? Like auth stuff, right? That was like the main way that we talked about it. Yeah, so hashes are hashing is a process that's made up of hash functions. So just like we had that functions that mixes something up, that takes a piece of data, it scrambles it up to a certain degree, which is understood by the hash function to spit something else out. To spit out new information, or to spit out a hash that that will serve primarily, from what I came to understand from reading, as an ID. So it is not the information itself when using it to refer to hash tables. It's basically it refers to a point on an index or in a list. Basically, it is the location of the information that you are looking for. That's what that hash represents. So a list-like structure designed to quickly hold and retrieve key data records. Record locations are created with hash functions that are mapped to a set of possible indices on a table, or the addresses that are saved in memory. So hashing was really cool, and I thought one thing that I really liked about it when I was doing more reading was definitely the parts that, like, the human elements, as far as resolving collisions, which I'll get into later, kind of comes in. Hashing shows up a lot throughout computer science. We used it in Beats, I know, to get our auth tokens for Spotify. We use it again in auth when we talked about it in class. Like I said, it takes a key, it scrambles it with a very specific algorithm, and produces an index that it uses to sort the key, to sort that information into a hash table. And it sorts it when it creates when that information goes in and gets stored. It's kind of like when I was thinking about it, I thought a lot of like being at the library and like the Dewey Decimal System. One way that is very approximate to the Dewey Decimal System is the way that hashes get made up, which I will also talk about that down here, but I want to talk about the functions real quick. Functions are designed to be simple, or rather the best functions, shall we say, are simple and quick. They take a key, which is usually a string or an integer for a data record, and return an integer memory address, which is the location of the data that will go into the index where the data is actually stored. It maps a key from all the keys. It maps the key from all of the possible slots. Think of it like a bookshelf. I'm going to draw it out in a second. But it finds an empty spot on the bookshelf and puts it there. If it can't go there, then it puts it in the next closest position, so that even if your hash isn't, when you go to find it using the hash, if it still even if it's not in that location because of a collision, it's still a close approximation of where that location is. So if you have something like a million users and you're trying to find a specific one, it'll still get you approximately to where you need to find it, which saves a lot of time and space as far as big O stuff goes. The algorithm scrambles the key to get an index. The function needs to be specific, i.e., the same input must yield the same output. We talked about that a lot in class too. When you mix something up, this is not randomized. This is not a randomization that happens. It's a very specific scramble that ultimately the output of that scramble is a much easier way to find the information that you're looking for. So if you're in a library and there are 10,000 books in the library, it's much easier rather than sorting all of the books by title and going through every single book. If you can have a number like a Dewey Decimal number, it makes finding that book so much faster. Like I said, the best hash functions should be simple and efficient. They should also distribute values evenly through the table and minimize collisions. So collisions are, like I was saying, was like that was when a hash for one thing results in the hash function results in two similar outputs for or two identical outputs with different inputs. There was the example that I found used an example of a hash function that takes a name and sorts everyone's so you can find their names. It was a function that returned a number between 1 and 10. So if there were 10 slots, you would find your number in 10 places. So we just go like this. And then we go 1, 2. So this whole thing is your hash table. So the example I found online was assumed that we were taking a name and assigning each character for that name an integer value, right? So 1 for A, 2 for B, 26 for Z, etc., etc. Then you add the value of each character in the name. You take the sum and modulo 11, and to get an integer between 1 and 10. So let's say we have a name that yields us, and this is where I'm really bad at math, and I'm going to kind of pull some stuff from thin air. So let's say you have like Cory, and when you add all these sums together and you modulo 11, you get like 4. So when you're sorting all this stuff in the hash table, you go 1, 2, 3, 4, and Cory goes here. Versus, say, let's have Rob, and when you have Rob, it comes out, you add up the numbers for the characters, you modulo 11 to get your integer of 10, and you get 3. So then Rob goes here. By running this hash, you are getting this number. This number is the location of data. This is the data. This data isn't obvious in the real world, isn't just going to be Cory or Rob. It's going to be a key value pair. It's going to be an object or a list. It's going to be a lot of different things, but it makes it so that you can quickly find the data that you're looking for. Does anybody have any questions so far? Don't everybody? Great. Great. Glad that we're on the same page. So a collision occurs when when you hash your data. So like let's say we put in Pratik. And when you run our hash formula, right, where you take all the numbers, sum them together, modulo 11, and then Pratik is also 3. This is called a collision. And it happens and the more thoughtful and elegant your hash function, the less frequently that this will happen, but it will definitely happen. So Pratik can unfortunately cannot go in here because Rob is already here. There are a couple of different ways to solve that hash tables use to solve collisions. One they are called open addressing and closing addressing. So open addressing revolves around what a technique called probing. It happens in a couple different ways, but what probing essentially is says that if Pratik cannot go in hole number 3, then we move on to the next index in the array or the list or whatever we're working with. It moves on to the next slot to the right and tries and sees if it can go in there. It can't go in this one, unfortunately, so it moves to the next one. And it sees that this slot is empty, so it throws Pratik down here. And like I said, that's called linear probing. It's a resolution for collisions. If there's a match that isn't available, it checks the next location on the right until it finds an open index. It uses a loop, which is important to think about for Big O. And there are some pros and there are some cons to it, which I'll talk about later. But one thing that really, really, really is important to think about when it happens is that it causes clustering, right? So now this whole thing is all bunched together. So the next time that we, let's say, have Alex, I don't know if Alex is here, but let's say Alex also were to come to 3, right? Well, now we would have A up here, and I'm sorry that this is starting to get so crazy. He can't go in 3, can't go in 4, can't go in 5, so he goes in 6. But you have to iterate. As you're going, you're iterating through the loop. You're iterating through each of these, or you're working your way through each of these positions, which means that each time that you end up with a cluster, then it means that you're getting farther away from O of 1. That's an O. Which is find the slot, get the number, find the slot, and put it in. And you're starting to get into O of N territory, which is obviously, less ideal. You want to like I said, you want to avoid clustering as much as possible. There are a couple of different ways to handle this. I'm going to go ahead and erase this real quick. Another way to solve the probing is to use what's called quadratic probing. There is math stuff, but essentially, if a hashed index is filled, what you do is square the number of indices you move to the right. This helps spread apart the distribution of filled slots. So when you have something like this, and 1, 2, 3, 4, 1, 2, 3, 4. Right, and this is our guy, and let's say that we have Cory and Rob and Pratik. So if you did have Alex, you would look 1 to the right, and you would say, okay, this slot's not there. So what you would do then is look 2 to the right. You would square the number of times that you look, or you would multiply by 2 the number of times that you look. So I had to look this up, what the fuck I was talking about. But essentially, you work through, these is the order of the functions, so you're trying to find the next empty slot. And so this finds Alex's empty slot in number 6 in one fewer search than finding it by going 1 and then it makes it much more efficient. And if this slot were taken, then he would look again at this one 4 slots down, boom, right here, and he would theoretically go there, which also has the benefit of leaving these slots still open for the next time that there's a collision. Double hashing, hash the hash with is another way to do it. Hash the hash with a second hash function that cannot return 0, and then return all the addresses on the table. So there's more math stuff, which basically works with you would if there's a collision, then you would run a second hash function, which again, so right? Like an ideal hash is our O of 1. So ideally O of 1, if there's a collision there, then you would run a new hash function to hash your hash. There would be something in your function to like notify you and other people or whoever is performing the search. You would notify the program that you had to run this second hash program and tell it to run it when it's searching for that ID. But ideally, what the hope there is that by running the second hash function, you will find a different slot to put it in. And that you're still maintaining this kind of O of 1, O of 1, rather than having to go to O of n. That's the whole idea here. So this, like I said, this is called open addressing. There's some, where we go? There's some advantages to it. It can really optimize a table if you know the types, the limit on the type and the number of keys. So let's say that we were sorting let's say it was a very small table, right? And there's 20 people in our cohort, or 22, or however many it was. So we know we're going to need 22 slots. 22 people are going to get in there one way or the other. And it really efficiently optimizes space, because if we know that there's 21, or in this case, let's say 10 people, we know that there will be, as far as our space component, right? Time versus space. As far as our space component goes, we know that we will efficiently be using our space in memory, and that all of our slots will be full. It can be completely filled up, like I said, so space gets used efficiently, and it doesn't require an additional layer of data structures versus what our closed addressing will use, which I'll show you in a minute. There are some disadvantages, though, because it requires more complex computation on the time side. You're running loops, right? You're running these loops to find like the next available slot when you're fixing these collisions, or you're running an additional hash function, which is kind of screwing you up. Obviously, like this isn't such a big deal when you're working with 10 or 20 numbers, but if you're working with let's say you are a company and you have all the phone numbers of your 5,000 employees, that's going to be really bad. It's going to create some problems for surezies. Another problem is that you can't add new values, which means you have to build a new table each time you are setting it. And addresses where keys end up don't necessarily correspond to, and often and can occasionally not be predicted by its hash, right? So the thing that we were talking about up here, about how the same input is going to yield the same output, the hash function should be simple and efficient, should be distributed, blah, 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 all that stuff. The problem is when you run this hash function for Alex and you get 3, you're going to look at 3 and be like, oh man, that's not Alex. So you're going to have to look at 4, that's not Alex. 5, that's not Alex. 6, that's not Alex. So you are 3 positions away. You are twice as far away from where Alex ends up twice as far away from where you expected him to be. So if you're trying to do your like O log, whatever, this might not always work, because you might end up super far away from where you think that you will actually be, especially, like I said again, in that scalability issue when there's 5 or 10,000 items to work through. I'm going to erase this. Groovy. Okay, so that's open addressing. Does anybody have any questions? Cool. Good deal. Yes. Oh, one last thing I wanted to talk about. I remember. I talked about time, working through the loop and finding an opening. Oh, this was an example that I was going to use, but it turns out that I just drew it. It worked out better when I drew it all out. Time, we talked about this. It takes time to loop through to find an empty opening. However, it's not necessarily working through an entire loop. So this, right? So if it needs a spot here, and it needs to, and if this spot is full, then and this spot is open, then it just drops them in here, and it doesn't need to loop through the rest of the items in the list or in the array. Let's see here. The more, numbers. The more slots that are filled, though, the longer and slower everything, the search to find an open slot or the search to find what you are looking for becomes, right? So if we're looking, like I was saying earlier, when we're looking for Alex and we expect him here and we find him here, the more slots that are full, the longer it takes to find the data that you're looking for, right? Because we might not actually be looking for Alex. We might be looking for Alex's profile, which contains addresses and birth dates and social security numbers and all that stuff. It could take a very, very, very long time. Let me see here. Closed addressing. So what closed addressing is uses modulo, or it uses another function basically to create a whole new layer with empty slots if ever there's a collision. So let's say, use our example here, right? Oh my gosh, this is so perfect. It uses a method called chaining to resolve collisions. Each slot layer is like a link in a chain. That's a way to think of it. That holds more than one record. And if your layer is full, then you dig down to the next layer. Think like Inception. You dig down to the next layer because you know that slot is where your information is, and then it's just a matter of how deep down do you need to drill to the next layer to find what you're looking for, to find the data that you're looking for, to delete it or insert it or whatever, to find that slot. So you're thinking of these links as data structures that hold keys and records, and each one, instead of thinking of it as just like kind of a slot like we drew up here, it's actually a bucket, and it goes way down here like this. We use linked lists to point to the next key. It uses an additional data structure, linked list, to point down to the next key down in the bucket. So if instead of using our closed addressing, we're using open addressing, what we're doing instead is, so if Alex comes in and says, hey, I'm supposed to go in number 3, we say, okay, number 3 is full right now, so you're just going to go down to the next layer. And Alex will still be in position 3, but he's going to be living on an extra hash table, or I guess in this instance, this bucket here becomes, instead of the slot pointing to a specific item or a specific object like Cory or Alex, instead this slot points to a linked list where the first position on the linked list is Cory, and the second position that it points to is Alex. So it will come to 3, it will look and see that Cory is there, it will say, okay, what's the next point on the linked list? What's the next layer that we're drilling down to? It drills down to the next layer, and it sees Alex there. Advantages here, it's much, 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 much less work on the back end as far as insertion and deletion goes, right? You're not iterating through loops. You're not really doing a whole lot of this. You kind of are, but to a much smaller degree. So instead of having 10 slots, you're just drilling down to the next slot down. It is much less. There's much less computation stuff going on in the back end because you're not iterating through a loop to find a whole slot for Alex to go into. It also has room to grow and add more data, right? Because you can, let's say that the next person that comes along is like Gabby, right? And Gabby is also, when we hash her name, we also get 3. However, so we go and we look in our hash table, we see that Cory is currently in position 3. Okay, so we're going to drill down. We see that Alex is in position 3. We drill down, okay. And we can drill down again until we and be like, okay, there's Gabby. She's going to go there. There's lots and lots and lots of room to grow. while it is easier to work with on the back end as far as insertion and deletion goes, it exponentially increases memory and processing, right? Like it's not this precise thing where we know exactly there's going to be 10 or 20 people and every hole will be filled. What's going to end up happening, especially if we try to do this for a lot of people, is we would have, Pratik here, and then Rob would come along, so we need to have Rob. And then we'd have over here, we have like Shazad, and Shazad's over here. But then along comes Brett, so we put Brett there, and now Brett is here. And then over here we have Chloe, but then we have to add in, Dan, and then you add in like Anderson. And I recognize that this whole thing looks like oatmeal, looks like literally hash, and that's because it is. It's very messy, and it's also not very space efficient because there are scenarios where your hash functions are popping people down to the next layer in the bucket without checking to see if these spaces are full. These spaces are still held in memory. There's just nothing there. They're null, but like that area is still saved in memory. But we keep drilling down rather than finding places on this level to put our new entries. So we're going down 2 or 3 layers. So it's really, really, really not memory and processing efficient. Because, like I said, many slots are never going to get used. Inefficient hash functions as well. Or very large amounts of data can create very long chains, which greatly result in greatly decreased efficiency. So while it is nice on kind of the back end that we can just say, oh, we don't have to iterate through our loop, we just pop you on down. There's a world where you're going down, 3, 4, or 5 layers. At which point, are you really being more inefficient when you're running this function you're running your hash function to find out where jam is, right? And you're finding spots for jam. Jam's supposed to go here, and there's all these like people here. So now jam goes in here. So are you like at this point you've now gone down 5 layers. You could have gone 5 layers this way, but jam would have gone here, and all he would have had to do is move over 1 position. Chaining and probing. Okay, before I finish that section, does anybody have any questions? Cool. Chaining and probing. So hash table implementations all revolve around 3 different methods, right? Searching, inserting, and removing. So they all are going to work. Let's start again here. Right? So all hash table implementations include 3 basic methods: search, insert, and remove, right? You're looking through each of your slots to find what you need. You're working on some level by looping through to find the position that you're looking for, using the hash as a guide though. So it's not just a straight up loop through this whole array. We think we know where it's going to be because the hash gave us this approximate address. You're hashing the key when you're searching. You're seeing if it isn't at the index, and then you're probing until you find either the empty slot if you're inserting something, or the item that you need if you're searching to retrieve that information, or if you're trying to delete that information and making that slot whole. So like let's say that we're looking for Alex again, and there's also Cory and Pratik and Rob here. You're working through until you find Alex, and when you do, you are pulling Alex's information out because you need his email address to send him an email about something. Oops, not that one. This one here. That's how the probing works. with chaining, you hash the key, and then you search the data structure for that index or the linked list until you dig out the key from the barrel, right? So let's say that you're looking for Alex, and or let's say you're not looking for Alex. Let's say you're looking for Karen, and Karen is here. You run your hash function that tells you that Karen is in position 6. You look in position 6 and see Alex is there. You say, okay, well, I'm not looking for Alex, I'm looking for Karen. So you drill down one layer and you find Karen and you say, there's Karen. I'm going to email her a link to buy these new linen sheets. Inserting, you're going to hash the key. You're going to put it at the index generated, and then you're going to probe it until you find the available index, right? So same deal. You're running your hash, you're finding out where it's supposed to go, and then you either put it where it's supposed to go or you put it in the next available index. With chaining, you hash the key, and then you hash the key, and then you save it down here, and we're going to put Gem's information, and Gem is going to go down here because when we hashed him, he was in 6. We're going to add him to 6, and we're going to point Karen at Gem, so we know that if it's not Alex, it's Karen, and if it's not Karen, it's going to be Gem. Same dealio with removing. However, there is an extra layer to it, which means that you need to set up an indicator to let. Additionally, you need to set an indicator and make sure that all of your other corresponding functions, right? Because theoretically, when we're writing our hash functions, it's not something that is going to be just me using or just you or just our department. It's going to be information it's going to be going through a lot of hands. So you need to make sure that it's very clear that there's an indicator that the index is now empty for future probes because other people running other hash functions running on it might be setting at a starting point that, well, we know that 6 is full, or we know that 5 is full here, right? So we're not even going to start at 5. We're going to offset, and we're going to start our hash function at 6 when we start using this hash table, because we know that 5 is empty. 5 is full. But if 5 becomes empty, then you need to make sure that the programs and the systems that you're using know that 5 is empty, so it can go and knows that Rob's not there anymore, and you can drop Will in here. Boom, there he is. Okay, does anybody have any questions about this so far? Great. So I did want to talk for a second about something that I've discovered called a direct access table, right? A direct access table conceptually is a one-to-one data structure hash table that specifically maps records to a corresponding key. So you're imagining an array of phone numbers, right, for everyone on Facebook. Because of a one-to-one relationship, that the key value there being like, Cory Spicer having a phone number of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because of that key value, you will know that there's only one Cory Spicer. There is only one phone number. So all you have to do is find the hash, is get Cory Spicer's hash, and you will instantly have that phone number. You don't have to drill. You don't have to down to the next layer. You don't have to, let me pull this up. You don't have to drill down to the next layer. You don't have to probe to find the correct spot. You just know because there's a one-to-one relationship, and it works as O of 1. Even though the issue with this and why this works in small numbers and not in really big numbers is that space gets really big really fast. Tables are created using the maximum value. So like, let's say there's 22 people. So we would have 23 values available to us for indexes for everyone in the cohort's phone numbers. The problem is that it's not really scalable when you do it like in a large with like a large sample. So like the idea of having the phone numbers of everyone on Facebook, which has 1 billion users, you need a table that is 1 billion slots big, which is really not ideal space-wise, and you'd probably be better served having a table that is half the size, but that you can drill down to. It would probably make things much more efficient. Yeah. Hash table use cases. They're great in situations where we need to locate and retrieve a record of collections in millions or billions of possible entries, like databases, finding specific items in a computer's memory, those types of things. They really help us. They really help us point to our hash functions, especially really good hash functions, are really good as at pointing us in an approximate location on a database where we're going to find this information, right? And so if this hash table here is our database, it's going to point us to an approximate location, and it's just a question of how deep do we need to drill or how many spots do we need to move over. And then so it greatly shortens the length of time to find what you're looking for. Hash table time complexity for search and deletion is O of n as a worst case scenario that has to loop through every single index to find its slot. But a nice thing about hash tables and a nice thing about probing and drilling and chaining, is that as soon as it finds a slot, it's done and it doesn't need to run the loop anymore. So you're not running for each loops here. As soon as it finds what it's looking for, and as soon as it meets that condition, your function is returns. Apparently really good hash functions can get down to O of 1. I wasn't really able to wrap my head around it, but I bet Pratik knows the answer. So yeah, that is what I learned about hash tables this weekend. Yeah, does anybody have any questions about anything?
Can you scroll down to the hash table use cases paragraphs? Cool. Thank you.
Okay, I'm gonna turn off the recorder here.